All right, welcome everyone. This is session number 8 for ANZ coders, and for this particular session, we have Poya talking about machine learning. And as I said before, my voice is rubbish at the moment, so I'm going to disappear and let Poya take control. Poya, over to you, mate.
Hello, everybody. Good to see you. So today we're going to be talking about machine learning. Before we start, I'm going to give a bit of a heads up. Sorry, everyone. Sorry, everyone. Just a small technical difficulty. Okay. So before I start, I just wanted to give a word of warning. I believe the neighbor's dog has been abandoned or something. So if you hear, profuse barking, please do. I do apologize for it. So with that, I'm just gonna get started. I'll just get this sharing going on. And here we are. So predictive analytics and machine learning 101. You'll see my name there. I am a Redify consultant, and on the side, I've been working on Neuromine, which is, I guess, a service for doing machine learning. Now, I think the first thing I want to talk about is what is prediction. And I think that's an interesting question to answer, because it sounds like there's some complicated definition for it. But when it actually comes down to it, it's something that we do all the time. So, you wake up in the morning and you see some clouds, and the first thing you're thinking about is, well, actually, it's probably going to rain today. And we do that sort of thing all day long. We, for example, see the traffic and predict that I'm going to be 40 minutes to work instead of the usual 20. Even typing on your keyboard, it's something that you've learned, and your fingers have almost like automatically predict where they need to go next to type the word you're trying to type. This one is interesting. So I found this picture, and I thought to myself, if anyone ever sees this creature here, probably the first thing you're thinking, besides the fact that this is awesome, is that you're going to run the other way, right? Like the first instinct is you're going to run the other way. But why is that? Because none of us have seen this creature in real life. So why is it that we would be afraid of it? And that's, again, learning kicking in. This is where we've connected the dots. And because we know, for example, it's got horns, we think, okay, horns are dangerous. Or we see that it's got muscles, so it must be strong and able to hurt. So we have been able to, based on our learnings throughout our lives, be able to connect the dots. And even though we've never seen this creature before, we know that it's dangerous. So what is learning, or what are the components of learning? It's, again, this is this idea of connecting the dots. We made observations, and we're able to connect these dots. It's not exact. It's not something that you always get right. It's a process, okay? So it's not something that you figure out once and it's done, but it's an ongoing sort of process. And with it is involved experimentation and kind of making mistakes. You fall off your bike 10 times, and then you learn from that mistake and from trial and error. But then what is machine learning? If we're talking about learning as a human, then what is machine learning? And I found this definition. It's a very scientific definition, and something that I suppose as developers we probably just roll our eyes at. But I think it's important and it's helpful, in capturing what is machine learning. So in this case, it says a computer program is set to learn if its performance at a task in T, as measured by P, improves with experience E. So that machine learning has these three elements. There's some task you're trying to complete, and with experience, your performance or your how you're performing at that task improves. And if an algorithm can do that, it's said to be learning. I'm sorry, I don't know who this man is, but good quote. Now, as developers, on a given day, we're constantly writing logic. We do stuff like this all the time. We write, if temperature is low and if it's overcast, and if it rained yesterday, then it will rain today, or at least there's a likelihood that it will rain today. And it might seem, if you haven't really worked with machine learning, it might seem that, artificial intelligence is about writing lots of logic into the computer. But if you think about it, this logic, the actual learning happened with a human, right? You as a developer or whoever figured this out they did the learning, they made the observations, they figured out these steps, and all we've done is just put it in a computer. So with machine learning, what we're trying to do is shift that learning to the computer, obviously. So what are the different types of machine learning? I guess there are tons of different ways of doing machine learning. There's so many algorithms, but if we were to group it, there is two classes really. There is unsupervised learning, and here what we're trying to do is we have a lot of data points. We don't know anything about them, and we're trying to make groupings. Okay, we're trying to see which data points relate to each other. It's kind of like an exploration of your data. The typical example of this is customer segmentation. Whereas traditionally you would have thought that actually your customer segments are, young people between 20 and 25, and then, middle-aged people and whatever it might be. With this sort of learning, you might actually see insights that you wouldn't have seen otherwise. You might actually realize that actually that young customer and that really old customer have more in common than you would have thought. And the other kind of learning is supervised learning, and this is probably one that you've seen more often. When we talk about neural networks and many of these things, this is what we're talking about. And really, the idea is that you have a model, you have a predictive model which you train, and then you give it some independent variables. For in that example, it would have been the temperature or whether it rained yesterday or not. And then you predict some other dependent variable. So this is whether it's going to rain today. And the process has got these two phases. The first phase is using previous data that you've observed before to train that model, to generate that model. And then the next phase is, now that you have the model, let's start making predictions for new independent variables. So I think the best way to, it's a lot of words, and I think the best way to really see how this works is to work through an example. And I wanted to show you how a decision tree works. Decision trees are kind of one specific class of machine learning amongst many others. So let's think about a problem where, let's say we have an object, and about that object we have 3 pieces of information: whether it has eyes, the number of legs it has, and whether it's furry or not. Okay, let's say those are the 3 bits of information we have about an object. And we want to predict whether or not the object is a cat, a person, a chair, or something else. And let's say this is our training data. So one training case might be that, if it has eyes and it's 4 legs and is furry, I know that it's a cat. Okay, so this is the data I'm going to use to train my model, to generate that model. And all those cases are sort of follow the same kind of thing. So in a decision tree, the first thing we do is figure out what is the one property that is the most important in making that prediction. And that's kind of the guts of the algorithm, is figuring out what is the most important property. In this case, it's the number of legs. It's the most telling of all. And we'll say that there could be less than 4. If there are less than 4 legs, let's go to this one branch to the left. If there are exactly 4, we'll go to the middle branch. And if there are more than 4, we'll go to the right branch. Now, at each of these points where we've branched off, we'll decide what is the next best property to now decide, or predict what that object is. So it so happens that if there are less than 4 legs, the eyes are actually the most important thing. And if it does have eyes, it's probably a person. And if it doesn't, it's something else. If it has exactly 4 legs, then furriness becomes the most important. And if it's furry, it's probably a cat. If it's not furry, then it's a chair, or it's probably a chair. And if it has more than 4 legs, that's just creepy. So we've generated this model now. Now we've done our training, and now we're able to make predictions about data that we haven't seen before. What's interesting about decision trees specifically is that they're very human readable. So you can actually, once you generate that model, you can actually look at the model and make meaning of it. Another type of algorithm that you would have heard a lot about is neural networks. And there's some really fun facts about how neural networks work. So I'll just briefly explain how that works. So the idea is simple. The idea is that the brain, or in this case, the machine algorithm, is made up of some neurons and some connections between these neurons. A neuron is just like a bit of information, and you can think of it as a light switch. So we can say that it actually turns on or lights up, and then that light kind of transmits from that neuron to other neurons via these connections or synapses. The strength of the synapse, in this case, I've shown it with a thick or wide arrow. That connection determines whether or not the next neuron will fire or not. So the top one, because it's a weightier connection, that neuron fires, whereas the one at the bottom doesn't. So you're probably thinking, okay, how does that relate to that input and output? So a full neural network might look like this. So you have some inputs, which is whatever information, your independent variables. Then you have some other number of hidden layers, or it is referred to as hidden layers with some number of neurons, and then your outputs. Okay. So the way this works is, when we're training, we give it a set of inputs from our training set. Okay, in this case, it's on, off, on, and then we just let it, and all these connections initially are just random, have random strengths. So we let these sort of connections pass all the information all the way to the end, and it so happens that when we do that, we get on and on. Then what we do is we compare that to what it should really have been. So in this case, that it should actually have been, the actual observation was it should be on and off. So we realize that second output is wrong. And the training process involves us going back to all those connections and just adjusting them ever so slightly to get us the right answer. Okay? So it's about the whole training process about adjusting those weights so that given some inputs, we can get the expected outputs, or at least get close to it. And we iterate this over many, many data points. In reality, there would actually not be just on and off. There would actually be numerical values associated. Okay, great. Now, this is a very interesting picture. Actually, before I get to this, I'll explain what the experiment was. So these hidden neurons actually are referred to as something called feature detectors. So actually, they end up detecting features in your input. So the experiment was they trained a model with a bunch of images of people's faces, and then they used the weights after the training was complete. They used the strength or the weights on these connections from the input going to the hidden layer, and they used those to generate new images. And what they came up with was this. And when you look at this, two things you'll notice. So first thing is that some of these are really freaky, like the one up here. I'm pretty sure that's in a horror movie somewhere. But the second thing you will realize is that what's happened is that those hidden neurons have learned something about various features of the face. So the top two, for example, have learned or are sensitive to the eyebrows. The next two are sensitive to the eyes, and so on, the nose, and so on. And you can just imagine, I mean, this in the case of a person's face, that's very obvious to see what it's doing. But if your data points is for example, information about a customer, the neural network is actually learning some really complex relationships within your data. The other example is the XOR function. So if your input is the XOR function 0 and 0 gives you output of 0 and so on. I actually personally played with this and did training with this, and then I started plugging in numbers that are not just binary, because the machine learning, you can learn real numbers. I started putting in 0.1 and 0.1 and so on. And what I came up with was this. So what's happened is that model, not only has it learned about the binary information, it's learned all those values in between. It's created a smooth curve. So at this point, you're probably thinking, okay, great, this is all fancy and images and XOR, but what do I care? I'm a developer. I need to think about things that apply in day-to-day life. So let's talk about some of these applications. So one clear application is image and voice recognition. This has been around for a long time, and many methods have been used, and machine learning is a particularly good way of doing doing image and voice recognition. And this is something we use daily. Another application is in health. It can be used to do medical diagnosis. For example, you can get the information or the properties of a cancer cell and then predict whether that cancer is, what type of cancer it might be. Another interesting one I came across was patient readmission. So for example, a lot of times hospitals will release a patient and that patient actually ends up coming quickly back to the hospital because they get sick very quickly again. And that's a huge cost to hospitals. So you can use the machine learning algorithms to sort of try to predict which patients are at risk of coming back quickly. And in those cases, ask them to stay longer or whatever precautions you need to take. Personalization is a huge one. An example is targeted marketing, figuring out what sort of marketing best suits as a part of your customers. Recommendation engines, this is a big one. Most sites or a lot of online sales sites will now have some sort of recommendation engine, which generally uses some form of machine learning to predict what you're likely to buy next. Churn analysis is another one, which is figuring out which of your customers are at risk of churn, and lead scoring, which is kind of similar. Another area is finance. Payment fraud detection is a really good example. Credit card fraud, for the longest time, have been using these algorithms for detecting credit card fraud. Stock price prediction. This is probably more borderline, gambling, but certainly there are software out there that try to do prediction of stock prices using some of these methods. Inventory management, so it's trying to predict how much inventory you're going to need, not just simply looking at the last month, but using a whole lot of factors, including seasonal factors and so on, to try to predict more closely what your inventory needs are going to be. And then sales prediction, kind of a similar thing. Anomaly detection is another one. So there are software out there that basically help you manage a server farm and sort of minimize the number of false positives, if you like. It's very easy to set thresholds on things and say, hey, if my RAM usage is getting to this point, there's probably going to be a point and I need to raise a flag. But in reality, a lot of those might be, false alarms. And so with machine learning, you can start to capture more accurately when your hardware are going to fail. Intruder alert, trying to tell the difference between a person walking through your house or a cat. Many email and other form of spam filters use machine learning to figure out, they actually read through the content of the email and try to figure out or predict whether or not that's actual spam. So all of this sounds really good and great, and there's all these applications. But what are the challenges? Well, there are a few challenges with doing this. It's not just magic and always works perfectly. So one of the big challenges, and probably the primary challenge that you're going to face when doing prediction and when doing machine learning, is having good data. That's really hard to do, and that's really a problem across, I suppose, many data fields. The biggest problem is you just don't have enough data. A lot of these algorithms, for example, neural networks, decisions, they really feed or do best when you have a lot of data. And when you don't have a lot of data, what you end up getting is not going to be obviously as good. Another problem is having unrepresentative data. So let me give you the example of credit card fraud. If all your data set is about legitimate purchases and only a couple of or a handful of cases of fraudulent activity, then obviously your model is going to really be skewed towards the successful or the non-fraudulent cases. So that's something you need to watch out for, and there are methods of trying to mitigate some of that. Another challenge you can run into is that there might actually not be a real relationship in your data. And this is probably the scariest one, because you're not always going to know if that's the case. Sometimes you will create a model and using your training data, it seems to perform really well. But then you actually go to use it in real life scenarios, and it turns out it's actually really poor. And that's because the relationship that you thought was there, or the data that you provided, there really wasn't a good relationship within that. The other form of sort of challenges that you're going to run into, and this is, these are probably where many scientists and mathematicians are spending their time trying to improve, is this generalization. So let's say you have a whole bunch of data points, and you want to create a model that best describes those data points. It might be that you come up with this really nice graph that almost goes through all of those points, and you might look at this and go, "Oh, great! I've really created a great predictive model." But then you go to use it in real life for a prediction for a point that's way out there, and that's going to perform horribly. And in fact, if you'd originally just drawn a straight line through those, just get the mean and take a straight line, your prediction would have been a lot closer. So this is a case where you've really specialized for those training data that you had, but it's not actually performing well with, when you're trying to use it for real life scenarios. Another problem is something that's referred to as hitting a local minima. So you might do some training, you might create, a model, and you say, okay, I seem to be doing pretty well, and if I train any more, it seems like I'm actually doing worse. You can see the slope starts going up. So you stop training. Little do you know that had you pushed on, had you trained further, you would have hit a much better, error. So just briefly, I also want to touch on some of the software and services out there that you can start playing with, or you can learn about. So traditionally, there are some open source sort of things that you can look at, and our programming language has, I want to say, definitively become the de facto standard for doing machine learning and all the other statistical work. So that is something, and you will find that a lot of other software, including, for example, the Azure machine learning, uses our components to be able to extend the functionality. And there are some others out there. Weka and Orange are just a couple of those. And in terms of software, sort of traditionally, we've had these applications like Mathematica and MATLAB, which are, I suppose, more geared towards academics and data scientists. And then some sort of enterprise level software, such as SAS, and I think even SQL Server Analysis Services has machine learning components. This has been sort of the traditional way to do these. But over the last few years, a lot of other sort of services have come up. I think the first one that I'd seen, and interestingly, I don't hear about this, excuse me, I don't hear about this as much, is the Google Prediction API, which is actually a bit of a black box. It's not known what algorithm, what they're using under the hood. Likely they're using a whole number of things to get you the final result, but it's just an API, REST API. You give it your data, and out it spits predictions. Azure ML is obviously a lot newer to the scene, but if you haven't played with that, and if you want to play with this space without having to really code too much or at all in a way, this would be a good place to start, because it will give you an understanding of how the data flows and what algorithms you might use without having to understand the inner details of these. So Neuromine, I have to do my shameless plug. That's also a simple service that you can use for doing predictions. There's others like BigML and Wise.io. And then what I've noticed in the recent years is that more services are becoming very specialized. So they will do machine learning associated with a very fixed sort of space. So for example, algorithms.io and infer.com really focus on lead generation and customer analysis, and they're not kind of like this broad generic machine learning platform like Azure ML. So in terms of resources to look at, personally, like a course that I did on Coursera was Geoffrey Hinton's Neural Networks for Machine Learning. there's other courses on there, and they're free. They're a bit more maths heavy and go into a lot of detail, but I think at least the first few lessons are great as a broad understanding of some of these topics. And then there's other Pluralsight courses and other free resources for learning R and so on. And in terms of data, if you're looking for data that you can play with and test out some of these ideas, these three sources come to mind. So UCI Machine Learning Repository, you'll find that it has a lot of data sources. And in fact, I've seen in other places, so for example, Azure ML, actually for some of their samples, they use data from this data source. Kaggle, you might have heard about. It's a community of data scientists, and basically the idea is that different companies can come with real world problems and submit it to Kaggle, and then they basically run a competition around it where different scientists can offer their algorithm or their results, and the company basically obviously can benefit from getting that knowledge. But they also share that data source, so you can definitely use those. And then something like the ABS is great for also getting data that you can play with. And with that, and I believe I'm a bit short. Yeah, I'm done. So I will now switch back to the screen and take some questions.
Fantastic. Yeah, good stat. Nice, Poya.
Thank you.
All right, so let's have a quick look at some questions for you. And we have one so far, though I'm hoping the audience is madly typing things in at the moment. So how about Python comparing with R? You can't just say R.
R. To be perfectly honest, I don't know enough about Python to compare it. I do know that it is obviously used. To believe it or not, I actually use C#, and people would probably make it funny, but you can use any language to do these. So I think what I've found R is that over the last few years, it's become more and more popular for these. And one of the, I guess, attractions of R is that there's a lot of components that others have built that are shared, and so you can just use those within your applications.
Okay, let's see what else we got.
It's fine.
Very few questions. I'm assuming.
Yeah.
I'm assuming the lack of questions is because everyone's just sitting back going,
What is he talking about, or he explained everything
oh,
perfectly
wait, here we
well.
go. So, what kind of things have you personally applied machine learning to?
For me, a lot of it has been, I guess, yeah, some of these data points that I've found on those sources that I talked about. So a lot of it will be around things that I've tested with is like detecting types of cancer, doing some of the data that you will find on that UCI source is credit card fraud and that sort of thing. So I've played with those. It's hard. I think one challenge is actually finding, I guess if you're in a company actually trying to do it for a production thing is finding the right fit for it. That's always a challenge.
Mm-hmm. So Neuromine you mentioned before as your particular project. What's different about that from other things?
Yeah. So with Neuromine, I guess the goal that I had was to make it again, making it really sort of a black box. So I suppose even if you're using something like Azure ML, you still have to understand something about, what these algorithms are, how I need to split it and do my training and validation, that sort of thing. Whereas with something like Neuromine, I really wanted to make it so that, you just upload a CSV file, click train, and then just start making predictions. So cutting a lot of that customization out of the middle. Now, of course, if you want to get a good model, there's going to have to be some experimentation. So if you're taking that out of the equation, you're going to not come up, I suppose, with a perfect model. But sometimes a perfect model is not needed, if that makes sense.
Yeah. Okay, so there, in the chat channel it says, in most of the cases when we do machine learning, there's lots of features, which is fair enough. How How do you decide which ones to use in the model building other than trial and error and pretending that data scientist means anything more than someone who pokes things until it looks okay?
In a way, I think that's the key word. It's ultimately it comes down to trial and error, and then just seeing in certain spaces you kind of start getting an intuition for what properties are important. One interesting thing about things like neural networks is that they're actually taking a bit of that work out of your hands, right? So that whole idea of feature detectors, that layer of hidden layers, is that it is figuring out what parts of your input are important and what things it should ignore. But obviously, you can always make better models by putting better inputs, removing the ones that look like they're not really contributing.
Okay. And any thoughts on how ML and Azure ML will impact the data mining feature that SSAS has had for a few releases now?
That's a very good question. Probably one that I can't comment on at this moment. I think Azure ML it's still new. It's still something that it still remains to be seen how exactly people are going to use it. But yeah, not a good answer, I know, but
Hey, it's an answer.
yeah, it's a nice something.
All right, cool. Anything else? Audience members? That's you guys.
Yep.
And we do the wait 20 seconds while the streaming catches up to what's actually happening, which is cool. And if not, we just want to say thank you, Poya, for prepping the session and doing that talk. It was very cool. Always good to get something different like that, and then try and figure out how we actually apply this to our own stuff.
Yeah. No, I realized there wasn't a line of code for an ANZ coders conference, but it's good for a change.
Everyone's been putting all their code in slides and then pretending that they're coding, except for Aaron, who did JavaScript sort of, but then even then chickened out and did most of it in slides.
Yeah, gets a bit more risky online, I guess.
All right, well, thank you, Poya. Let's round of applause. There it goes. And
thank you. Thanks,
warning
Richard.
for you, Mitch, in particular, no spoilers, dude. Otherwise, I have to insta-ban you.
Great.
All right, we'll take a short break. I need to definitely get a drink. The throat. But we will be back shortly with Daniel doing the secret of transactions and async await and nerdy goodness like that. So that'll be on in all of 10 minutes. See you shortly.
Thank you.